All right, good morning, folks. I am here at the school recording this on the Monday. And so this is kind of going to be how our lectures will occur. I will have these notes posted on Google Classroom for you to look over. And then from there, you can just kind of follow along. If you'd like, you can print them. They are already done. So I will have the completed notes for you. So mine are going to look different from what's posted already. We're just going to go over this. You can make your own side notes. If you'd like, I can post some blank notes. Maybe I'll post both. That way you have both to go with whatever you want to. So if you want to print them off, you can do that. If you need a printed copy, please let me know and I'll print off a copy of notes for you and you can grab them from the school at some point. So we're going to get started on the electrochemistry unit. And we're going to get started with topic 1, which is reduction and oxidation half reactions. So our single replacement reactions are a good illustration of electron transfer. So electron transfer just means electrons are being transferred, and all those reactions share a common feature. Ions are converted to atoms, and atoms are converted to ions. I guess one thing I need to be aware of here is that you cannot see what I am saying. So ions are converted to atoms, and atoms are converted to ions. So we know that, let's put up to our pen, is that ions are something such as sodium, which is Na+, and it's converted to an atom, which is now Na, and then we just want to subscript that, which would be solid. Also, too, atoms are converted to ions, so we could have something such as Cl2, and it is converted to an ion, which would be Cl-, which would be aqueous. For balancing purposes, we would need to have a 2 there, but we don't need to worry about that too much as of right now. So the first example we see in this diagram here is our example, the reduction of aqueous silver nitrate to silver metal in the presence of solid copper. What we see in this first image here is that we have our aqueous silver nitrate, and we have this roll of copper here. And then we have an arrow. This is showing what's going to happen, what's reacting, and the copper is dispersed into the aqueous silver nitrate. What sort of things do you see occurring in that reaction? All right, probably the most obvious one that we're seeing here is that color change from a clear solution in the aqueous silver nitrate to a colored blue solution in the silver nitrate, which would now be, what's that called? Copper nitrate. So we're going to go into some of the reaction and what's actually occurring here. So we have a non-ionic reaction, a total ionic reaction, and our net ionic reaction. So on the completed notes, you already see what's happening here. And what is happening is that we have a single replacement reaction. As we said, if we can go up here and back up here, single replacement reactions are a good illustration of electron transfer. So our net ionic reaction is going to be copper is bonding onto nitrate. This is going to be copper 2 plus NO3, and then we have a 2. This is an aqueous solution plus Ag, which is our silver. And we said that it got converted from an aqueous solution to now a solid solution. Just to make sure our balancing is right. So 1, 2, 1, 2. So that's our non-ionic reaction, which is essentially meaning that we don't have ions, we have compounds. We could break this down further, though, in which we have our total ionic reaction. And then this, if we look at here in the first part, is we have a solid in copper, we have aqueous of silver and aqueous of nitrate. Nitrate should have a negative charge right there, so we'll put that in. And then what this produces is copper 2 plus, and this is going to be aqueous plus 2 NO3 minus, which is also aqueous. And then I want you to take a moment and think about what our last one will be. That is correct. If you had 2 Ag solid, you wouldn't start off bound with your coefficients. Obviously, these would get put in after. So if we'd assume that this isn't here and this is not here for now, and then we would start balancing, and we know we have to have 2 nitrates to balance out the 2 nitrates here. So we would have a 2 and a 2 there, and then our coppers are fine as is. When we begin to look at our net ionic reaction, what changed states? Let's start with the left side. So we have copper, which went from a solid to an ion. Switch to green here. And we have silver, which went from an ion to a solid, which is an atom. Did any change occur with nitrate? Take a moment, take a look. NO3 minus, both in the aqueous state, there was no change. So we'll cross those off, and then we would just rewrite our total ionic reaction as what is left over. So I have copper solid plus 2Ag plus produces Cu2 plus, 2 plus, which is aqueous, plus 2Ag solid. All right. One question I can see coming up is that, do I need to have the twos still intact here? Yes, you do. What we're saying is that we need to have 2 parts of silver ion, which I forgot to put my aqueous. 2 parts of silver ion need to react with 1 part of copper solid to produce our copper 2 plus ion and Ag solid. We have a diagram here on the right. I will move that just a little bit so we can see. So what's reacting is we have our Ag plus, the silver ions. They're going to react with the copper solid in the presence of the nitrate. And then what's going to happen is that Ag is going to replace the Cu2 plus. So every 2 Ags, so we have 2 silvers, 1, 2, is going to send this Cu2 plus out of there. All right. Take a moment. Think about that. Just don't want to rush too much here. All right. We are going to move on to half reactions. So half reaction shows only half of our net reaction. There are 2 types of half reactions, which are reduction and oxidation. So I'm going to use my highlighter here. I'm going to highlight reduction and oxidation. These are going to be huge terms that we're going to use a lot throughout the unit. There are some acronyms you can use to remember. So I will write those out here. So my personal favorite is oil rig. Kind of picked a poor spot to write this. So we have oil rig. So we have reduction and oxidation. So O is going to be oxidation, and R is going to be reduction. Reduction. And then I is going to be is, and then L is going to be loss. And G is gain. And then that's just an acronym to remember this point here. So reduction refers to the gain of electrons. So reduction is gain. Oxidation refers to the loss of electrons. So oxidation is loss. On the completed notes, you also see another one, which is Leo the lion. Leo says grr. So we will take a moment and we will write that out as well, which is Leo says grr. I don't like using this one as much. I prefer oil rig. Oxidation is loss. Reduction is gain. This is just another one for you to use. So loss of electrons is, what starts with O? Oxidation. So Leo is loss of electrons is oxidation. So G is gain of electrons. So O is oxidation, R would be R E D U C T I O N. Gain of electrons is reduction. All right. So there's just a few acronyms to help you remember those. I'm going to take Leo the line that says GER though. I'm going to group it and shrink it just so I have some space here. So group, and shrink. All right. Again, I like the oxidation is loss, reduction is gain. If you want to use that, one of these has to be helpful for you to remember. So again, I will use oxidation's loss, reduction is gain, oil rig. All right. So we're going to look at a reduction half reaction. So we're going to use the one from above. We are going to use silver. So for our reduction half reaction here, we have Ag plus, which is aqueous, and it is converted to Ag solid. These likely look familiar to some of the bonding unit that we covered in Chemistry 20. Now, you have a positive ion here, and it needs to be converted to an atom. So my charge on this side is +1. My charge on this side is 0. What can I add to this side here to give me Ag solid, so silver solid as an atom? Well, this is reduction, and reduction refers to the gain of electrons. So we're going to have Ag plus gain 1 electron. We're going to put that here and put that here. And we're going to leave that alone for now. We also have our oxidation half reaction, which is Cu solid. Oops, don't put a plus there. If you're looking at the completed notes, you'd probably wonder why I put that. And this produces Cu2 plus, so copper 2 plus as ion, and this is now aqueous. And then oxidation refers to the loss of electrons. So oil rig oxidation is loss. Electrons are lost. So this would be plus 2 electrons. From Chemistry 20, you would likely remember that we need to have our electrons balanced. So I have 2 electrons here, and I have 1 electron here. How do I get to a common factor? Our shortest and easiest way to do this is we're going to multiply the number values together to get our common factor, which is going to be 2. So I will put a 2, I didn't put it in red, up here. And now everything inside these brackets, let me just switch to a highlighter here. So everything inside these brackets now is doubled by 2. I need to write down my net reaction, and then what gets crossed off are my electrons, because if I have 2 electrons here and I have 2 electrons here, I don't need 2 electrons on both sides. I will put 2 electrons on this side to start, and I'll put 2 electrons on our other side to start. I just put this line here to show what our net reaction is. 2 electrons there. I'll do this in black now. So 2 electrons plus 2 Ag plus, which is aqueous, reacts with what else is on the left-hand side? This copper solid here. So plus copper solid. And our products are Cu2 plus. What's the state of that? Just above us here, it is aqueous plus Ag solid. So we will have 2 Ag solid. Put my plus. Now, silver went from an ion to an atom. Oops. Oh, I guess a little confusing. Be aware that I put a plus there. The plus is referring to plus 2 electrons. So the 2 silver ions became 2 silver atoms. My 1 copper atom became 1 copper ion. My electrons cross off, and that is how we find our net reaction. All right. I am going to stop the screencast here, just to kind of give you a break, let you review that page, and then we will hop onto this one here, which is creating half reactions from a simple redox reaction.